Okay, my name is Ji-hoon Kim, and I was the person who sent you many nagging emails about this comparison workshop, so thank you for not yelling at me yet. So I'm going to talk about the experiment that I have been doing with the radiating molecular cloud particles in a simulation of dwarf galaxy formation. So this will be the outline. I will hope to convince you that in a parsec resolution, high resolution era of the high resolution galaxy simulation, we have to think about the physics of molecular cloud, if not the physics of individual star particles more carefully, so that we can resolve those physics more well in a galaxy formation simulation. So what am I talking about is the following. So contemporary high-resolution galaxy simulations have a typical resolution of, say, 10 parsec or even more, 3 parsec, or even less than 1 parsec resolution is not rare in these time for example, this Bernard et al. Paper already 2 years ago achieved 0.8 parsec resolution in a whole galaxy merger simulation. So it is crucial to think about what kind of more proper molecular cloud physics in this parsec resolution simulations, because not only because of its spatial resolution, but also because of its temporal resolution. If you think about the time step corresponding to that resolution, it's about 10,000 years. That resolves the typical time scale of the molecular cloud. That means we are resolving the evolutionary stage of the molecular cloud. So we have to be careful about what those molecular clouds do in their early ages, in their later ages, for example, after the supernova explosion. So I'm going to describe briefly the model that I'm going to use in the simulation using ENSO. So this is a simple one-slide summary of how I am forming the molecular cloud particle. So I'm going to keep using the word molecular cloud particle instead of star particle, because I am actually trying to represent the molecular cloud particle characteristics in my simulation of maximum resolution 3.8 parsec. And the mass that we are going to place when the cell is effectively gene unstable is about 1,000 solar mass. So it's trying to describe the individual molecular cloud particle in our simulation. So, and the feedback that we are employing is, of course, the title says it has the radiation, but it also has to include the supernova feedback. So the lifetime of my molecular cloud particle is about 6 million years. 6 million years is the lifetime of my molecular cloud particle. And during that time, in terms of the supernova feedback, it doesn't do anything until about 4 million years. And at around 5 million years, peaking at 5 million years, is the supernova explosion that corresponds to the type 2 supernova. So it's a slightly different from compared to other models that people have been including in their galaxy simulation, where right after the birth of the star particle, the thermal energy is injected as a thermal feedback or the supernova feedback. And also there is a mass return of 80%, sort of describing how the mass is recycled back into the interstellar medium, so it can be sort of recycled again and again. And as I said, until 4 or 5 million years, it doesn't do anything in terms of a thermal feedback. So what it does instead is the UV photons coming out and being ray traced in the simulation. So we will probably have, for example, in our typical dwarf galaxy simulation of, say, galaxy mass 10 to the 11 solar mass, we have about 10,000 molecular cloud particles. But with a really sophisticated and smart algorithms for the ray tracing, we can actually do the ray tracing of those many molecular cloud particles on the fly, and that is what we are doing. So we are employing 16 electron volt monochromatic photons, and that interacts with the hydrogen by the photoionization and photoheating and some primitive form of radiation pressure that doesn't include the infrared rescattering process. So that's what we are doing between 0 million year and 5 million and during the lifetime of this molecular cloud particle. So that's what we have been implementing, and this is in line with what people recently have been claiming, that the early stellar feedback is important, like Hopkins et al. And Greg Stinson et al. So we have tested this model on an isolated dwarf galaxy that has a mass of 2 times 10 to the 11 solar mass, and including less than 10,000 radiation sources. And because we were not able to evolve this entire galaxy from scratch to, say, some dynamical timescale of these galaxies, we were able to evolve this system, already well-evolved galaxy, adopt that galaxy, and then impose this resolution and sophisticated physics, and evolved it about 30 million years. Although we see a suppression of star formation suppression of about 25%, I'm not going to say too much about the implication of the radiating molecular cloud particle in a galactic context. I'd rather focus about the other things that I'm going to talk about. So I'm going to mostly talk about 2 different aspects, each of them representing a simulated observation that was possible by this powerful post-processing tool YT. And it's not only a visualization tool, but also a post-processing tool. So I'm going to first talk about the escaping of the ionizing photons. So we have this integrated radiation field. For example, here, as I showed you earlier, this is the projected photoheating rate. And as you can see, there is a shaded region by this thick galactic disk. Yes, it's interesting, but let's step forward a little bit. That is the following. So because we have all these density of singly ionized hydrogen and electrons in the entire simulation box, what we can do is to make a all-sky projection from a individual molecular cloud particle and make a projected number density and projected neutral hydrogen fraction, and eventually a directional escape fraction plot. So as you can see here, for example, you're going to see a no photon in this direction, whereas here you can see a lot of photons coming out. So what this plot says is there is a thick galactic plane in the middle, and there is a nearby clump that blocks your stellar light coming out of this particular molecular cloud. And if you do this analysis with this post-processing tool for multiple times, there? Yes, that was the escape fraction, like a percent. So this was 0, meaning this is a log scale, so it's 1 escape fraction, 100%. So if you do this for multiple individual molecular cloud, then what you can make is the galactic escape fraction if you integrate it over a many different molecular cloud particle, and that's what you're seeing here. So I'm going to just play some movie. So here again is the photoheating rate, density weighted. So you can see where the most radiating molecular cloud particles are, and here what you're seeing is a location of high escape fraction molecular cloud particle that pretty much coincides with the high photoheating rate regions. And the size of this circle corresponds to the escape fraction. So you can see that most of the high escape fraction clouds are clustered together, not like dispersed everywhere. And you can see that the overall galactic escape fraction pretty much stays at around 1% over this 20 million year period, which is pretty much coinciding with what Nick Nedin or John Wise has been finding, although it's a little in a lower end because it's a massive galaxy and also well-defined galactic disk. And what I am finding also is that galactic escape fraction is mostly dominated by a few high escape fraction clumps. For example, if the galactic escape fraction is 1%, then what it means is more like 1% of the particle has 100% escape fraction rather than 100% particle has like 1% escape fraction. So that's what I am finding in this analysis. So if I draw these star particle, molecular cloud particle population in a plane of particle age versus escape fraction, this is what we are seeing. Actually, what I'm finding is that this high escape fraction cloud tend to be old. That could be because the particles are drifting away from the initially star-forming region to a lower density region. And it could be also because the supernova explosion peaks at around 5 million years. So here you can see that although most of the particles lie in the zero x-axis, what you can see is that the escape fraction generally rises as the particle ages. So at around 0 million year of the particle age, the escape fraction is close to 0, whereas at around 6 million years at the end of this lifetime, it's about 2%. So on average, it's about 1%. So I'm going to skip to the second simulated observation, which is to understand the star formation relation using this galaxy data. So as I said, I have a whole box data set of the number density of singly ionized hydrogen and also the helium, also the electrons. So what I can do is, rather than making this Kennicutt-Schmidt plot using just the gas density and the star formation rate density that you take out from the simulation, what I can do is to do the actual mock observation, making the H-alpha emission plot and also estimating the FH2, which is the molecular hydrogen fraction. So that's what I can do easily using this simulation data and also this tool that I'm talking about, YT. So this is the map and also the local maximum that I identified in this H-alpha or the star formation rate estimated by this H-alpha luminosity. And this is the H2 molecular surface density. And this is the Kennicutt-Schmidt plot. So as you can see, there are many dispersions there. And actually what I'm finding is that because I didn't explicitly employ Kennicutt-Schmidt relation in my star formation recipe, what I'm finding is that as you use higher resolution aperture or the smaller aperture to make this mock image or the mock observation, you can see a more dispersal of data points as you move to a smaller aperture. And that actually is what the observers are finding. So this is a M51 in a 0.75 kiloparsec aperture, and as you move to a smaller aperture, you are seeing a larger dispersion of the Kennicutt-Schmidt plane, if I may. So that is, of course, what is expected. And as you use more smaller aperture, what you are resolving is these two different population of molecular cloud, two different population. In that here, more to the lower right, is the cold gas that has a more higher molecular gas fraction compared to its H-alpha luminosity, meaning they are forming stars right now there. Whereas on the upper left, that population would mean you are emitting a large H-alpha emission compared to the surface density, meaning you are talking about a later age of the star cluster, not at the ongoing star formation site. So what we can think about is using, depending on which peaks to choose in your observation or a simulated observation, you are going to see a different population of molecular clouds. So if you are choosing a H-alpha peak then you are preferentially choosing the hot gas slightly off from the ongoing star formation site, maybe a little later stage of this molecular cloud evolution. Whereas if you're choosing the molecular cloud, a molecular gas peak, H2 peak, then you are preferentially choosing the cold gas. So that's what people have been doing in a simulation and also in a observation, and that's what I did in a observation. So in a mock observation. So this is the average for the molecular hydrogen peaks. So if you do this mock observation over the H2 peak, and then you find the value for the H alpha luminosity in that aperture. So that's what I did for this experiment, and the average for those peaks locates here. Whereas if you do the same analysis for the H alpha peak, or the star formation rate estimated from the H alpha peaks, then the average value is around here. So what you can see is, just as I said in this plot, you're talking about two different populations. So depending on which observational technique you're using, which aperture you're choosing, you are picking up two different population this way. So I'm just gonna say that that is what the observers have found. As you move towards a smaller and smaller aperture, those two average values bifurcate, meaning that below some resolution limit, below say 300 parsec limit, Kennicutt-Schmidt law really doesn't hold well, because you are no longer averaging over a different evolutionary stage of the molecular cloud, because you now have enough resolution to resolve the individual and different stages of the evolution of the molecular cloud. So I was in a little bit hurry for the second part, but I'm just gonna say that in this high resolution galaxy simulation comparison project, and also in general, we have to think about the realistic treatment of the molecular cloud physics in our simulations. And I hope I have convinced you, at least in this short amount of time, that combining this sophisticated molecular cloud physics and the post-processing tool, there are many intriguing mock observations, simulated observation that we can do. Thank you very much.